So hello everybody, welcome. Thank you for joining us both in person, and also welcome to all of you who have joined us online for the seminar. So as a part of the Dr. Kiran C. Patel Center for Sustainable Development seminar series, we have a talk today by Professor Armin Hafner. So Professor Armin is a professor in Refrigeration Technology at the Department of Energy and Process Engineering at the Norwegian University of Science and Technology, NTNU in Norway. So his main field of interest is refrigeration and heat pump technology with focus on carbon dioxide as a working fluid in these systems. Prior to joining NTNU, I think you were with a research agency in Norway, SINTEF agency for several years. And today I learned that he also spent, I think, one semester in India in 1992 as a student. So welcome back to India, and thank you for joining us.
Thank you. Thanks for the nice introduction. And yes, welcome to this seminar. And maybe before we start, I would like to know, have you heard about refrigeration before? Is somebody of you in the field studying refrigeration technology or mechanical engineering, energy technology? Who is energy technology? Who has background in heat pumps? Who knows refrigeration? So yeah, okay. So you are into it. So let's see. Yes, today maybe first I start also to introduce where I'm from. You see, Norway is on the northern part of Europe, and it's quite a long country. When you put from the lower part to the upper part and you turn around, you're below Rome in Italy. So from Italy to Norway is as long as from the southern part to the North Cape in Norway. So it's quite long. India is also long, but Norway is also very long. And Trondheim is very close to the Arctic, the polar circle. It's not, we are a little bit below. That means you will see the next picture, we have some daylight still. Because this is just some figures about our university and our contract research institute, SINTEF, which is located in the same place. We're working very close together. And you see the campus in the middle of the town, and it's also growing. And then this is a picture from the autumn of the main building. And as I said, we work very close together with SINTEF and build a cluster of innovation for the Norwegian society. What's the problem?
Your video is coming as a negative.
Okay. Ah, yeah. That looks funny. Yeah.
No, we restarted that by turning it on and
Ah.
if not, we can use the camera on the laptop.
Yeah. If you share your laptop, if you turn your laptop around, then
you can go ahead.
Yeah.
This camera.
Yeah, use that camera. That's fine. Yes, now you can see me. Good. So this picture is from autumn, as you can see, and then this picture is right now in the morning. Sun is appearing maybe at 9 o'clock, 9:30, and it disappears at 2 o'clock. So we're just coming across the horizon because we are so close to the polar circle. And in summer, it goes down there and it comes here. So it's the opposite. So you get payback in the summertime. So don't worry. Even if it's dark, it will be long days in summer. Yeah. But your contribution is really essential because we all need clean energy, as you know. That's in the daily news. Why do we need it? Because we need peaceful and a sustainable society. Without clean energy, it will never happen. That's the largest challenge we have right now. And how can we utilize clean energy, and what do we need it for? Most of all, food. None of us will survive without food. And you can imagine how much cooling we need for food to preserve the food. And especially in this country also, we could have much more food in the market if we can preserve it at the right time, at the right place. Also, the housing and transportation needs also cooling. to have a good life on this planet. And that's what we are focusing on. And today I will show you a little bit how we can do a transition from currently dirty cooling, what we're really doing, towards clean cooling. And it's not rocket science. It's just asking the right questions at the right time of the end user and those who develop these systems. Okay. So content of today will be, I bring you a little bit back in history when refrigeration started. It's also always nice to know where it all comes from. And then we look a little bit about energy efficient fluids, some architectures of these units, and some installations from industry. It's always nice to look how industry is doing it. So let's see. And as we are working with this Indie Plus project where you can join, and we will also have educational units around in India. Maybe you can join some of the other universities and just have a look. So what were the drivers to introduce mechanical refrigeration? It was, before people were harvesting ice on the lakes in the winter. And then this was kind of kept in the storage places. You see, this is a picture from Norway where people harvested ice in the winter and put it in the cellars, and then they could use it, and they exported a lot. Norway was the largest exporter of ice by the time, even to India, because the guys from England, they would like to have Scotch on the rocks. And the rocks came even from Norway all the way by ship. So that is not so sustainable by that time. But of course, ice is very sustainable. It's just harvested from the lake. And you see that the tons of ice which have been exported to Great Britain, it's about similar what we export in salmon today. So it's a lot of ice. And that's also one reason why Norway has a shipping fleet. It was all these ice exports which started these companies to trade with ice. And then later it came these kind of systems to make the artificial ice blocks. Like in the US, and still in the US, they're calculating refrigeration, tons of ice. They have not the SI units as we do with kilowatts and so on. They still calculate tons of refrigeration, which is tons of ice blocks. But most of all, beer brewing, that was the start of mechanical refrigeration, because with these ice blocks, you could not produce beer all year long. In the summertime in Germany, they couldn't produce beer. It was too warm. The Belgian beer is different. It has this other kind of process. It can accept higher temperatures. But the German lager needs lower temperatures. So that's why the guy, Linde, he invented mechanical refrigeration and made it commercially available. And he produced within very few years nearly 750 large ammonia units, which he sold all around Europe. So he made a fortune on that. And then he went back to university and studied low temperature refrigeration. When this Linde process and so on, that was after he left this business. It went on. But then he went back to university and studied the low temperature processes. Yes, so that was, and then the other stuff was transport of meat. Already by that time, meat was brought from South America to India, to China, and to Europe by boats, which had first refrigeration inside. Some with absorption, but also with mechanical refrigeration. You can see here is not for the non-vegetarian guys and girls. These are the beef pieces from South America, full, the ship full. And here you can see the refrigeration system was a CO2 system already by that time. Huge systems and very slow motion machines, like this is the steam engines, similar to those. Yes, that was the early days. Here you see these big machines in the ship. But then we had a journey. So until the 1930s, it was mainly these natural working fluids. It was mainly ammonia and CO2. And then there were some American guys, they invented something which we know all as Freon, CFC, that was heavily introduced with marketing campaigns and so on. And of course, it was a revolution because they could use copper tubes, and it was a lower pressure, less poisonous than ammonia. The leakage, ammonia is not difficult or not dangerous, but you need to have a tight system. And in the early days, sealing technology and all this is not like it is today. So today is no problem to have a sealed system, but by that time it was, and that was, they kind of used this as an argument and introduced this and made a lot of money on it. But as you all know, in the 70s, Molina and the other guy got the Nobel Prize because there was something on the ozone layer. And the good thing with the Montreal Protocol was it is the only or the first and ever protocol which was ratified within 2 years by all countries. So everybody understood we cannot cheat more because cancer and whatever, the ozone hole over there in Antarctica was evident. So everybody said, okay. But it was also because the chemical companies, they had the next generation of refrigerant ready. And the day after the patent was granted, yes, now we can go. Because then they could get 10 times more per kilo. They lobbied heavily for introducing the HFCs as a substitute for the CFCs. And then another 20, 30 years, we have been dealing with them now. But also by that time, see, by that time, we started in Norway in 1988, 97. The previous professor, Gustav Lonsen, he said, we need to focus on fluids which do not harm the environment, which do not introduce another problem, like we had with DDT and PCB and all this stuff. So already by that time, he said, we should focus on these fluids as well. So there was a start into this direction. And then there was the Kyoto Protocol, which focused on the global warming potential. But that took 7 years to ratify by many countries. And you see, US didn't join. You guys and China also not. They were not exempted for many to do anything. So Kyoto was never kind of the like Montreal Protocol. And that's why we are still kind of in that loop where the EU made a pre-start with the F-gas regulation. But then we have this Paris Agreement to the Montreal Protocol and this Kigali Amendment to really treat now with these F-gases, because that's the challenge now. If everybody needs these kind of fluids to provide what I told you, food, cooling, and all this cooling in houses or heat pumps and so on, we have a real challenge. I didn't bring that slide, but on a global total emission, everything, these F-gases are between 2 and 3%. That's a lot when you think about all the combustion stuff, everything. So still, only the emissions of these gases is more than 2% to the total contribution, which we could easily eliminate by just applying the technology I show you today. So there's an easy transition actually. So that's the question, why this F-gas journey? Is it really the best to society and environment, or maybe to a few companies or a few shareholders? That question we should think about. Please. Yes. It's these HFCs, all these HFCs, which before we had the CFCs, and it will come now in the next slides. Sorry. So these F-gases, what is the challenge? They have a severe impact on humans and the environment, and that we have to look into. The CFC killed the ozone layer, also people. Actually, it was very dangerous to be kind of in the same machine room like some of the CFC units, and some these mechanical engineers servicing the systems or operating the system, they smoked. They did not survive very long because the decomposition took place inside the cigarette, and this really poisonous stuff went straight into the body. So many died on that. So we have global warming of all these fluids. But what is more important now to understand, these fluids are not stable. Some are longer, stable, stay long in the atmosphere. That's why they have a large global warming potential, because it's defined as the period of absorbing heat and generating this heating. So if you have a substance which is very short life, per definition on a 100-year perspective, it's a very small number on global warming potential. So the engineer at these chemical companies, they got a kind of challenge. Please give me a solution which has a low GWP number. What they did, and I show you that in a slide. They now, these fluids have been known for many decades, but they were never used before because they were not so stable. But now it fits exactly for the kind of requirement. If they're not stable, they last maybe 10 days. On a 100-year perspective, the GWP value is very, very low, of course. But is it, by doing so, a green product? Or what happened actually with the product? That's the question. And that is not treated by any climate restrictions. It has to be treated by a chemical restriction, and that's coming out because it's decomposing to this TFA. That's the problem, and most of them do it. And this TFA is really not good. It's in the drinking water, it's in the mother milk, it's everywhere. It's not good. It's a forever chemical, not at all good. So, and we had this, our friends in America, they did a survey some years back, and 60 million different combinations. We are kind of in this supercomputer. They calculated a simple refrigeration cycle with some different combination of fluids. And what they found out is, there are only 27. That's the last, that's what we have. There are some hydrocarbons, there are some HFCs, some of these short life HFCs, CO2 and so on. So there's not much, so there's no kind of magic fluid somewhere. So that what we know, that's what we have. And we need to handle that. So it's very important that there is no new class. So I've lately been to Japan, and it's a pity because they spend a lot of money on development of new fluids. But according to this study, they should really focus on using the clean cooling instead of spending so much money in these fluids, because they all kind of have a challenge, as we will see in a minute. And also, if we do a refurbishment or a kind of retrofit of an old system, we have a challenge. If we use these new short life fluids, which are mainly flammable, while the old system was not designed to contain a flammable fluid from the safety point of view and so on, it's not a wise decision to just change the fluid. Also, the properties are slightly different, so it has to be adjusted. And then, so in some cases, it makes sense if the system still has some years of operation and it needs a fluid, yes. But for new systems, it doesn't make at all sense to use these fluids because they're very soon forbidden in Europe. And do you want to produce a system which you cannot sell to Europe? I'm not sure. Why should we do that? So this is the toolbox, actually. So it's here. Here we are working. These 8 elements. That's only what we have. And the further down, the more toxic. So we rather stay up here. Yes, and The more we go to the left, the more flammable. That's why. That's very flammable. So it's also kind of a balance always. Low GWP means high flammability. So all these new fluids are flammable. That's okay. We can treat that. It's not a problem. The design has to be in accordance. That's okay. CO2 is one exception. You can use it as a fire extinguisher. So it's not flammable. And now we come to your question with the what fluids are we talking about? You remember R12 that was heavily used. That's this family here. We have the R50, which is the methane. No fluorine and no chlorine. The more you go up, it's chlorine. The more you go to the right, it's fluorine. But all this we have a kind of ban now because the chlorine at all we don't need because that's killing the ozone layer. So we have this stuff is out, no discussion. So the only thing kind of left in the chemical part is this line down here, where you can see this 1, 2, 3, 4 stuff. That's on this line, according how many fluorine you give to the previously propane. Okay. But what is the challenge? This stuff transforms mainly to HF and TFA. That's exactly what we don't like. It's not stable. That's why it has a very low GWP value according to that definition, which is handled in all these treaties and all these international agreements. We need fluids with low GWP. That was what the engineer got as a kind of task. However, they are toxic. And this stuff, it's not sure, but there is a paper, and this guy, the paper got shut down. I mean, it's the chemical companies used a lot of effort to kill the paper, but he is a scientist from Australia. He has nothing to do with refrigeration, but he has evidence that there might be a chance that some of this stuff, when it is decomposing, is actually turning into R23, which has a high global warming potential, 14,000. Even if only 10% of this is turning into this R23, it means you have a GWP of 1400. And again, it's not the solution. There's more evidence on the way, but it's very hard. But it's also our definition, as I tried to explain you, the definition of these global warming potential values, that's the problem. It should be based on LCA, also on the production of the minerals and everything, which is ending up in the fluid and after decomposition. That should be part of the definition, how much it contributes to global warming, but that's not at all. It's just what's in the bottle, and that's all. So it's incomplete. So we need to include this in this definition. But it's like this, you see, well, the global warming is low. Don't ask me more. That's what you can hear from many. So again, Montreal Protocol is on the right. We have now we try to be down here because global warming is, this is the area where we should be at Origo. No, sorry, if I touch it, it goes, I should not do that. But there is hope. Yeah, so there is hope. The AFGAS regulation in Europe is under revision now. Yes, please. Yes. Whenever you have a question, please ask. Now here you have the CO2 equivalent reduction goals. So this is global warming, and this is ozone depletion. So we want to be at Origo at 0, both. Here we have these old freons, which both had a high global warming potential, but also killed all the ozone layer, because it's the definition of ODP is R11, that's why it's 1. Yeah, so and these intermediate ones, they were here, and now, okay, these were the HFCs, but now you see the 404A and all this stuff is also on the way out already in Europe, because of this F-gas regulation, where you need to reduce the total amount of emissions, and the higher the value, the less kilos you can sell. You need a quota for doing this. And that's why they are not in the market anymore. So now we're down here at R32. Whenever you buy a home air conditioner, mainly it's R32 nowadays. But you could do R290. Godrej has one, and the others as well. We're coming back to that. So there are alternatives. The good thing is, and there is hope, the F-gas regulation will also take R32, for example, because it's too much too high GWP value. And R32, on the other hand, is not degrading into TFA, but that's treated on the F-gas regulation, Kigali Amendment. However, this decomposition stuff is treated in another one. It is the PFAS restriction, which is under the chemical, it's a chemical restriction. It's not under the climate change anymore, because the climate change is kind of, the battle is lost. The definitions are in stone, but then they're not taking into account all the LCA and all this stuff. However, this restriction will allow to say, okay, if there are alternatives in the technology within a certain period of time, you're not allowed anymore to use these fluids because there are alternatives. And in 99.9%, we can show alternatives in refrigeration and heat pump technologies, which are maybe even more energy efficient than using the previous F-gases. That's our hope, and that's why we need you as engineers and to understand, yes, we can do it. It's actually very simple. We just need to do it and need to know that we need to do it. Otherwise, we're not getting rid of this 2-3% and all this poisonous stuff, which is accumulating up in your drinking water, in our drinking water, everywhere. Even at the North Pole, you can measure the TFA going up. So that's hope that this restriction is not killed by the lobbyists. It's of course under a heavy battle, but it's just a matter of time. Then, because people don't, you and we don't need it. You can all hear about it. Later you can find a link to the group who is preparing this restriction. It kind of takes many years to make all these new laws and all this. There's some hearings and so on, but it's underway. And of course, the chemical lobby may delay it, but they cannot. It's like sometimes we need to get rid of them. We cannot continue like we did the last 50 years. It's not possible. And we have the alternative. That's the good news. And non-jobs will be lost in the sector. That's also that there are so many opportunities. So nobody will lose a job here. Not a problem. The question?
Yeah. So in the previous slide, you are saying that every single refrigerant that has a fluorine compound has the potential to decompose into one of these TFAs. Is that the?
Many of them do. Those who do not do, they have still a high global warming potential. And those are treated under the F-gas regulation, the Kigali Amendment. While those who decompose, they have such a low value, they are kind of the favorites now. They try to sell them everywhere. But the challenge is they decompose, and we don't want to have these decomposition products in our drinking water and the mother milk and in our body. That is what we have to take care of.
And problem with the one on the extreme left, I think it was propylene. That one is the global warming potential. Is that the problem with that one? On the previous slide, you had one compound which did not have any fluorine.
Then you don't have any a very low global warming potential, and it doesn't decompose, and it's a natural fluid. Then we can treat it. The flammability we can treat. We need to treat flammability also with these other modern F gases. So the kind of requirements for the equipment is the same. Even if some claim, oh, the flame is slowly burning. That doesn't matter. It's flammable or not flammable. And then you need to have the precautions and all these safety measures. That's the same. So that there is no extra burden on that. And this kind of knowledge needs to be transferred also to the people doing service building systems, to understand that now we have new fluids which are flammable, and we need to treat them in a proper way and do the service in a proper way. And that is, if it's an F gas or a natural fluid, same. You need to do the same. So you can also read in this the writing thread of HFO and TFA in health from, you can download it yourself from r744.com. There's a nice kind of survey what they all collected, all the information. But why do we focus on natural working fluids? Because you and your customer, when you go out in industry, why should they invest in something which is a dead-end road? And it can be very short, very soon. And then the future is we should invest in a safe and sustainable development and real clean cooling, not just greenwashing and kind of, oh, no, that's not my problem if it decomposes. That's the disclaimer you can read in all these brochures. It's what's in the bottle. Yeah. So what are the fluids? What is our toolbox for the next 20 minutes? It's carbon dioxide. We can do hot water heat pumps. In Japan, they have 5-6 million of these hot water heat pumps in Japanese homes to make the hot water. In every home in Japan, they use mainly CO2 heat pump. Before, 20 years back, they had the gas-fired boilers or oil-fired boilers. And then in all these small towns and villages, there was such a huge emission of this exhaust, the combustion of this. So then, and by that time, they had a lot of nuclear power plants, which had a lot of the price difference between day and night was quite immense. It was maybe 10 or 20% of the cost in the nighttime between midnight and 6 o'clock in the morning compared to midday. So what the Japanese did, they developed heat pumps which utilize this power in the night to accumulate up all the water they need for the whole day. That saved a lot of emissions and also utilized the power available from the nuclear power plants by that time. And now they have another mix of that, but still the philosophy is good, that you remove fossil boilers to make hot water. I have another proposal for here. I will come back. Then we see a lot of commercial supermarket refrigeration in Europe and else. I will show you a picture. Many of these are transforming their systems to CO2, because often in a supermarket, it depends. You may have these standalone units, like you see in this, like you have at home, and then the heat goes into the room. And you need a huge chiller to kind of cool the room, because all this heat from the goods is just transferred into the room. And that's nice if you need heating in the winter and so on. But in summer, it's a really poor cascade system. And a poor heat transfer, first to the air, and then you have to cool the air and use a lot of energy. So often for bigger systems, you have a centralized system where you have one unit which has a much higher energy efficiency compared to small units. So then you have a large distance, and that's where CO2 comes into the picture. You can have the evaporator 50 meters away, and because of the properties with CO2 with high pressure, and so you don't lose much efficiency. That's a big positive thing. And also, we will see later, car air conditioning is also doing now with CO2 because it's very compact, very small. Heat pump chillers, I will come back. That's what we want to demonstrate in India, in hotels. In a hotel, you need cooling for room, for food and everything, and you need hot water. People take shower all the time, and this spa gets bigger and bigger. So then, and it's limited how much solar power you can put and so on, based on the specific demand. So that's where a CO2 heat pump chiller makes very much sense. I will show you a picture later on. When it comes to ammonia, you saw the picture from the brewery. Remember the beer guy 120 years back? Still, ammonia is also used a lot in India for warehouse cooling. Potatoes and all this, that they are cooled by ammonia system, large industrial systems. And ammonia is a brilliant fluid. It is very energy efficient. It's one of the most energy efficient fluids. And everybody has a sensor. Everybody has a sensor if the system is leaking. It's a few ppm you can smell, and you can leave the area. It's not dangerous. The dangerous thing is, and the accidents which happen, there were some accidents in China. The problem was the people were locked in the factory, and because they were afraid that people go out for shopping or they do not do the work. So they locked the people in, and the guy with the key, he went shopping. And when the accident happened, the poor people couldn't escape. But later ammonia was blamed to do it, but it was actually the safety around which failed. So ammonia is really a brilliant system for heat pumps and industrial refrigeration. When it comes to hydrocarbons, we can do most of it. In Europe, everywhere, the small fridges and all this stuff is all done by hydrocarbon. And lately also the residential air conditioning, like in your country, you can do it very nice with R290. R290, which is propane, that's the fluid for many, many things. Also commercial. Yes, please.
Why CO2 for residential?
Yes, we can do. It depends. If you have 5 daughters taking shower 3 times a day, then it will work. If you need to produce a lot of hot water, like in Japan, then we can use the cold side to cool the house and the hot side, like in the hotel, to produce lots of hot water.
I mean, fundamentally, from a systems perspective,
Yes.
the difference between CO2 and propane. I don't know.
Yes, what the difference is a bit the how the process is operating in the CO2 system. Mainly, it's a transcritical process, which is an optimum because heat rejection takes place at gliding temperatures, meaning you have a large triangular up there, which is, if you just reject the heat, is a loss. But if you utilize it, it's actually the opportunity. Compared to a conventional system, just condensing, where you need, maybe you don't need the heat, you reject it, so you don't need to go very high in pressure to reject the heat to the ambient, and you can make comfort cooling. Or vice versa, you reject it straight into the room at 25-30 degrees, which gives you the heat. And you can do this with condensing inside the heat exchanger. So it's a bit the process, but I'm not saying one fits all. We need to make the architecture for all the different systems according to the properties of the fluid and adapt it to find what is the best.
So let's say we have a CO2 based heat pump.
I show later some diagrams, then we can have a look if you want. But it's
COP different or CO2 and propane?
Yes, it depends very much what kind of duties you want to do with the system at which time of the year and so on. So if you have a combined mode, like for these heat pump chillers in a hotel, combined mode means You have always a cooling demand and always a heating demand for the water. And of course, you do this by storing in case it's a bit delayed and so on, it's no problem. Then you have a really high COP.
So what's the ratio of the heating and to the cooling?
The ratio is quite, it's a little bit more heating than cooling because the power to the compressor is
In India,
yeah,
50% of the electricity is for cooling,
yes,
and only 10% to 15% is for hot water.
it depends. If it is a hotel with a lot of spa and all this stuff, they need more hot water. I would guess.
Maybe,
But then we can have a combination. We can make a combination of a heat pump chiller here and maybe put an ammonia chiller as well. So find a good combination and combine these systems. That's always possible. Yeah. But it's exactly this kind of investigation an engineer, designer has to do. What is the demand hour by hour to find out how to optimize the system? How much storage do we need? How large or small can we make the system? What kind of energy sources do we have, and so on. So that's the analysis we need to do to get a happy customer at the end. And they're happy if the energy bill is low and the system is simple to maintain and to operate and to operate mainly. So coming back to this hydrocarbons, we see them also in high temperature heat pumps. For example, when you now want to avoid steam, or you need steam in a process, but you want to avoid the fossil burners because that carbon, we need to stop burn carbon, finished. So what can we do? We can upgrade heat from the chiller, 40 degrees, we can upgrade it to 120, 150. And there we can use hydrocarbons with the different properties, tune these systems, and then you can provide with a relatively good COP these high temperature lifts and produce steam, for example. So it's also possible. So we have the toolbox, we have the components. So let's have a look what we can do. This is just to show you a little bit the properties. When it comes to CO2, you see that the pressure is relatively more high than with the other fluid, R22, the previous one, or we are quite low on pressure, while here we are 1/10 more.
So this is low pass. So this is
Yes. You see at 0 degree, we had 35 bar in CO2.
okay, but these are actual numbers, not logarithms of those.
Yeah, so the evaporation pressure corresponding to temperature means at 0 degree, when you evaporate, it's 35 bar, while for the others, it's much lower. It's comparable with these two, but it's a kind of another line up there. And that we have to take into consideration. On the other hand, the density is also very high, so the pipe size gets very small. So weight-wise, the weight of a system is quite comparable, actually. So there is not much penalty on that. What is important to understand, when we go at low temperature refrigeration, freezing of food stuff, with CO2, we can go down to -50 and we still have 5 bar in the system, which is good. Ammonia at around -35, we are at ambient pressure. And then if we go lower, the challenges with the leaks, they go the wrong side and moisture coming in and all this trouble. So we're at very low ambient, low freezing temperatures, CO2 is the best choice. That's, I will show later some examples. Fish freezing and all this stuff on fishing vessels is done by CO2, because we can go down to -50. And at -50, if we have 1 bar pressure drop, we lose only 3 Kelvin in the evaporator. 1 bar is very much, it's a lot. Compared to the other fluids, you see it would be 30 Kelvin difference in the evaporator. But this value is quite low. You see at around 5 or 0 again, 1 bar is 1 Kelvin. which means we can allow large velocities, much larger velocities in evaporators and so on, very high heat transfer, even not penalizing too much on the temperature glide because of the properties. So that's good, because in other systems, we can see 10 Kelvin temperature difference or 5 Kelvin difference if the heat exchanger is huge because of the pressure drop and the properties of the fluid. Now with CO2, it gets very uniform. That helps. Another thing is the pressure ratio versus condensing temperature. And here you see low values. And for CO2, the pressure ratio, that's what the compressor is. I mean, it's not the absolute pressure, it's the ratio between suction and discharge. And there we have relatively low numbers for CO2, which means you can have a very high isentropic efficiency compared to other fluids who need a larger ratio to do the same duty, and then you're at lower values. So these are all the details. If you do just some simple analysis and you just assume it's always the same, the results are not the same. But here comes your diagram. Here we can see a traditional condensing fluid, which has the process like in here. While with the CO2, we need to go, and then we have this gliding heat rejection, and this is actually a loss. But if we do water heating, we can utilize it. And the next one, which we have a relatively high loss, is the throttling loss. When we throttle in the system. But we can come back to the challenges. The high refrigerant density is good. We can have a very small compressor and small lines, which is also good in industrial refrigeration. Imagine you have these huge capacity plants for freezing and so on, and you need insulation, and there is never space. But with a smaller pipe, you get sufficient insulation and the losses are minimum compared to a chiller system where you have to pump a glycol or so, which is huge, and the insulation. Pressure ratio is low, it's good. And we have very high heat transfer coefficient and specific pressure drop. So the heat exchangers can be very good adjusted, very high efficient. The challenges are as shown here, here and there. However, if you want to do heat pumping with CO2, that's why we have all this heat pump for hot water heating. But it's very important to understand you need to have a high temperature lift on the water side. That's important. So a low inlet temperature is crucial to be able to utilize it and to cool down the fluid before you do the expansion. If you still have relatively high temperature, then you should utilize this expansion work, for example, in an ejector. I will come back to that. So we can use this work for something in the system to increase the COP. With a simple device, not too complicated. Expanders and so it's too complicated. Failure rate is high. So it can work for megawatt systems where you have huge ones, but for small units it's too complicated. So let's also look a little bit on different evaporating temperatures now in systems. So I mean, from the banana down to the tuna fish, that's where we are working. And the tuna fish down there, when it is cooled by, for example, a CO2 system down to -50, then you put it in storage, and then you use air as a refrigerant. The Japanese, they have all this, the tuna storage is it's like these turbines compressing air, expanding and cooling it directly by air, which is more energy efficient than a vapor compression system, just for the storage. And you have also doing this COVID start with Pfizer -70 in the first run. That was because they put everything on dry ice. That was the -70. How to make larger system? Yeah, then it would have been air cycle systems for the storage of the vaccine. But luckily we don't need it down at -70 anymore. But that would have been a solution. But what is important to understand is the system architecture, and the freezing time and the duration of storage and the quality has a lot to do on the food, how to treat it. And often, I mean, in Europe, we don't grow bananas, so they are all coming by sea. And as you know from your experience, banana, it has a very short lifetime if the temperature is wrong. But imagine they send tons, millions of tons of banana from Middle America, Caribbean to Europe, and they can keep the temperature on a 1 digit of a degree. So why can't we do that with fish also, for example, to keep the quality? Huh? So one slogan like, do it like the banana. Sorry, I touched it again. So, but now I will show you briefly some systems where we do for low temperature, from -20 to -50 with CO2, which can be applied, which are maybe applied in India also, but they can. The very simple one is we have a primary loop here, or chiller, ammonia or hydrocarbon system, upper part of the cascade. And here down here, we have it's not a cascade because we have just a loop. Here we do a secondary loop with the CO2. So instead of sending the ammonia to the potatoes or to the factory where you have all this valuable stuff, or the person, you just send the CO2. Lately, we had an accident in our country as well. There was an ammonia warehouse storage place. A plumber guy came and he was supposed to put something below the evaporator, and he had good music and the drill was very good. So he drilled the hole and he drilled and drilled, and suddenly the ammonia came out. And the entire stuff in the warehouse, because of the ammonia leak, nobody got hurt, they went out and so on. But all the food, it was a value of 5 million euro. The food had to be destroyed because of the ammonia. With CO2, it would not have happened. CO2 will not affect the food. So that's why it's much safer to do it like this. And you can do this oil-free as well. So you just pump around and you recondense it in this evaporator, which takes the heat into the process. And you need this cold finger system in case you stop your process plant for some weeks or months. In some areas, they have some kind of seasons where they need the freezing, and then they need to wait. And then you need to have otherwise you lose the charge, because the pressure will go up so high and the charge is gone. If you keep it cold, it's no problem.
Significantly increase the capital cost.
But talk to your end user. I think he is convinced because of safety. And this has also a lot of backup capacity. In case you really have a challenge here, you can always vent a little bit CO2 and you have cooling capacity. For example.
Well, I have visited some of these potato villages.
Yeah.
There are different kinds of customers, and all kinds of customers in India. But the ones that I have visited, they don't even know what system they have. They don't have maintenance.
Yeah.
They have nothing.
Yes. But
they have algae growing on their cooling towers.
Yeah. I see. There's a lot of educational efforts need to be done. Yes, and knowledge, awareness.
They're open to education, but they're not open to opening their pockets.
Yes, but I think you can tell them, look, if you do a proper maintenance on your cooling towers and so on, you save a lot of energy, which is money in the pocket. Yeah. But that's an opportunity for startups to provide this kind of service, and some of them do it, and then they sell the saving. Half of the saving they get as an income for the next 10 years. Something they do like this, the deal. Then it works. Yeah, this is one example. Or we can look at, this is one in the market from Japan, where they use ammonia as I just showed you, and they pump the CO2 for the factories in whatever, even ice rink and so on. You can do like this, and the ammonia is very compact in the middle. It's a very low charge because they have also an indirect system towards the heat rejection or the heating up of the secondary loop there. So the charge is very much reduced and it's half the power. Another way is then to introduce a low temperature compressor, first stage of a cascade system. And then you can utilize, you could even utilize the CO2 here at the lower level. I will show that later. But again, we have a second stage system, which is maybe already existing, and we just put the CO2 system in the bottom. And yes, it's very energy efficient. Challenge is only if this one fails, then this one cannot work. That's the problem. And if this is ammonia and here is CO2, you should not at all have a leak inside this heat exchanger, because then you get this powder. The whole system is kind of destroyed because they react ammonia and CO2. This
as a liquid or as a gas?
It's liquid here, and then it's evaporating, and that's the good thing, because it makes it very compact, and there's a huge amount of heat which can be taken up.
So, but when it expands, there's a increase in the volume.
Yes, but then the compressor takes it. In this case,
Wouldn't it be better if it's a large system, like for example our campus, right?
huh?
So wouldn't it be better to just chill the water and circulate the water?
No, I would rather send the CO2 in the pipes and suck it back, and have these evaporators in the different air handling units where you need the cooling. And you could have 1 or 2 centralized CO2 systems, for example, where you connect all these evaporators and where you need the heat. And that place you put the heat pump, and to collect all the heat from all the buildings by having a network on CO2, similar to this. And then that pipe would be much smaller compared to the chilled water pipe, and the pumping power would be 0. Because the CO2 will come back because it condenses in the condenser. Well, but the other pipeline is also not very. It's also not cheap. It's a large amount of metal. The other one is less metal, maybe same kilo per meter. I think we are into something. We are doing this now. We have a project. We try to do this in like a campus complex, actually, to make the transition away from water-based loops, pumped loop, towards the infrastructure with CO2. This will take 2 decades to make the transition, because you need to build satellites slowly, where you have the small kind of air handling units, which are then DX, and then later you connect them all together. That will work, because in total we can save energy, because pumping power is quite heavy on these loops. This is an example of such a compact ammonia freezing package with CO2. They can go down to -50, -55. Then we are at the triple point. But that's very efficient for industrial freezing. You need fast freezing. Huge amount of products need to go to these blast freezers. Then you need low temperature. And then if we do this like this, we can have 2 temperature levels, actually. This one is supported by the compressor, so we can go down to -50. While the other one, depending on the condensing temperature, you can pump to your chillers. So you can, in all the production facility, you can have the CO2. We just lately built they built a chicken slaughtery in our place. Then they have no water loops in the factory, only CO2 loops. They collect all the heat, different levels, and then they utilize it on the hot side. No pumping power. when it comes to all CO2, so of course we can do that. We can have a two-stage system where we have the evaporators at the very low temperature, and then we need the two-stage. Then we should consider heat recovery or ejector, which comes in the next slide. The good thing, as I showed you before, because of this triangle, we can produce 90-degree water without any auxiliary heater. That's always the selling point we need to understand. Where do we need the cooling, and where is the heat? What kind of heat do we need? That's very important to find this customer. Where is somebody who wants to pay for that 90-degree? Then you have a case. Then the selling is easy. This is an example on a small fishing boat in Norway. They had previously R22, as you have in this country also. This was the R22 system. Inside the same space, they put the CO2 system, and they could implement even a bit more capacity because it's more compact. What happened is they could freeze more tons per day fish, and it was faster. It was these plate freezers were faster because they can go lower on temperature. What happened? The crew, they complained. The captain was happy because they could get more fish through it and it was good. But the crew complained because they had no coffee break or no tea break anymore. Before they had to, you need to wait until it's frozen. But now it was so fast, they have non-stop work. This is typically how these freezers look like. Here you put all the fish, and then it's frozen within a short time, and then the next batch comes in. Here is a system at CERN in Switzerland. You have heard about this collider collector stuff, and there are some detectors. The detector has $7 billion, and it needs to be cool. And we need to treat it like fish because this silicon, it cannot be warm and cold and warm and cold. It needs to be cold. And now that they change away from the HFCs, and they use now CO2. So they pump the CO2 through the detector. They pump a lot more than is evaporating, so the heat transfer is very good. The first 30% is used, and the rest is just pumped, and as a safety also. And now we also use the CO2 system to recondense the CO2 before it's pumped back into the detector. And the challenge is the evaporators are at 100 meters below, and this unit is on the ground, on the surface. But it works nice, and it is now under construction, and they will replace all the detector cooling with this kind of system. Yeah. Now let's look at commercial refrigeration. Supermarkets. There is one test unit in India, but we hope soon more. But this is the way you do it with a booster. They call it booster system because typically you have a freezer and a chiller, 2 units. If you do all in one, you can call it a booster because the low temperature is boosted into the other unit, and then you don't need 2 different fluid, 2 different condensers and all this stuff. So we have a low temperature side for the freezing and the medium temperature for the chilling. That's how it is connected. And typically we do -5 to 0 for the chilling part in the evaporator. And the good thing is, previously you need to make the room at 2, 3, 4 degrees. You need to go to -10 in the evaporation. Means you have a lot of moisture on the evaporator, defrost all the time, a lot of heat in and out, and takes a lot of energy. With CO2, we are not doing superheat inside the evaporator. That means we don't need to go so low. We can rather spend this surface to provide a uniform temperature, and then we can run very close to the freezing point, meaning many times they don't need to defrost these evaporators, maybe once a week, just for safety. But if you do evaporation around -1 on the fin, there is no -1. So then the water is running out, it's not freezing. Big advantage if you know how to do it. But this is why you don't do superheating with CO2. Then you get very high suction pressure and high energy efficiency. That's the difference compared to other fluids and system architectures, which we are used to. But if we think about it, it's easier like this. And we see many markets are going to these systems. And another way would be, this is even more simple. In the last 10 years, when we made some systems or supermarket chains, they introduced a series of systems. Oh, it's too complicated. And the service people, oh, too complicated. So that's why we focus on make it more simple. So we have an ejector to utilize this expansion work in the summertime, but in many parts, even in North India, it is rather cold in the winter. And remember, when there is no pressure, and then the ejector will not work, and it has no meaning. So that's why we developed a system there. When you have the cold temperature, you don't go to this expansion device, and so you go straight with the liquid to your evaporators, because they can deal with that. It's already liquid. And in the summer, and then the suction goes just through this device without maybe 0.2 bar pressure loss, 0.2 bar, but that is 0.2 Kelvin in difference. So it's not the problem. That's the beauty. If you have a high pressure system, you can really deal with this and you don't lose much. So that is now, some supermarkets will do this now. And we try also one of these systems in India. It's very simple. It looks a bit complicated, but there's some heat recovery, but it's not complicated. And the separator and the evaporators, and it's good. It's very simple. What we also want to challenge, and we have challenged the biggest supermarket company here, but they have been bought by somebody else, and now it's a bit a pity. The chiller for the supermarket. Typically, it is a double indirect system, meaning you have the water loop for providing the 12/7 water. Then you have the refrigeration system, and then you have the heat rejection loop towards the cooler. So you're penalizing the system everywhere. What we can do, we can go straight with CO2, DX into the air handling units, and we can do the heat rejection to the ambient, also directly with CO2. It's non-flammable, it's easy. And we can use a little bit water on the last part of the heat exchanger, really to use that wet bulb temperature to really subcool it before we do expansion. And we calculated forth and back, and we found out that if we do this on an annual base, the energy consumption is equal compared to the double indirect system with a HFC unit. No, and then we did not use any fancy ejectors and anything. It's just a simple one. So there's a huge potential, even in this business, to go in, especially pumping power, long distance, and all this stuff, insulation, pipe size. There is a chance. So there's an opportunity. And now this is the hotel. The hotel needs a lot of water, and then you store the water, because it's always some periods in the morning and there's some peaks. So you store it. And on the other hand, you have the cold water, which in this case, we circulate the cold water and have a two-stage evaporator to cool down the water in two phases. One is an evaporator which is in a natural circulation, gravity loop, which is the one the evaporator, the compressor sees. Let's say 45 means 10 degrees C. Because maybe the water comes back at 15 or something. No, it's coming back more with 20. Let's say we have a staging of some of these coolers also, so it's relatively warm coming back. So we take the first cooling down to 15 in this evaporator, which is the one the compressor sees. And the second one, reducing it further down to 10 by the ejector. Because our ejector is a small compressor, actually. It's driven by this gas, but it's able to suck a lot, to do a lot of pre-compression. That's what we do. So we boost the suction pressure of the compressor quite dramatically, 5, 6, 7 Kelvin. That's COP. That is really money at the end. So we can do very efficient cooling, and we do a very efficient heat rejection by heating up water. That's what we always want. We want to sell both sides, and then we have a super COP. Sometimes we may have a challenge here because this water goes forth and back. And if it's a charging, the cold water goes in, pushes the hot water when it's used, and then we charge again. So it's never 100% stratification. So for recovering of this, we found out that if you divide the gas cooler into 2 pieces, you also do kind of your water heating in 2 stages. Then you can recover some of this mixed water while mixing it with the cold. The cold one is preheated. It's unified with what is kind of lost, and then it's heated up to the hot side again. By doing so, you can secure that the hotel manager is not calling you on a Sunday afternoon, which you don't want. That's one solution. Yeah. So this is what is implemented in many hotels now, and it will be in many, because this is, yes, this we will do in India. In Europe we have already, but now we will do it in India.
Where is this?
In Goa. It will be, it's under construction now. It will be ready after Christmas, early spring. It will be there.
So this is how do you work like? You are from a research institute.
Yes.
How exactly you work with the hotel?
Yeah, it is our project. I will show it on the last slide. I will show it, but we are helping vendors via our partner institutes, IIT Madras, Bangalore, and Kharagpur, and BITS Pilani, and all this, SIFT, helping find vendors who are interested to learn, who are interested in picking up new knowledge. We help them to build the systems. They take the full responsibility, but later they are able to do it 100 times, 1,000 times. That's our aim, to help them in the design and implementation, commissioning. And we also implement a little bit more measurement equipment, which we pay for. So we have all the data we need to explain to others how to do it and not to do it. That's the aim of the project. So now we can go a bit quick. Car air conditioning. This was the first car with air conditioning 80 years back. Actually, it was in the back. It was cool. Huh? The evaporator was in the back side, because mainly they had a driver. Huh? So the guy or the lady was sitting in the back. Then Gustav Lorentzen, he said, we can use CO2 smartly by adjusting the high side pressure. It's not anymore the valve, which is here. It's not anymore controlling the superheat. It's just controlling the pressure. How much charge do we move from the low side to the high side? Because, as you see, if the charge is too low, your COP is poor. If it's good, it's perfect. If it's too high, you can get a little bit more, but you pay a lot. So there's always an optimum high side pressure in these processes. That's the mantra. And important thing is to understand that we need to cool it as much as possible to get this efficient. And mobile air conditioning, it started, more than 23 years ago. This was an R12 system from existing BMW. And this was the first prototypes, handmade, same size, and then put in the bench. And the surprising thing was, oh, we are nearly equal. We're even better in some cases, which was impossible when you just do some state point analysis of these two fluids. Because of all these properties, heat transfer, pressure drops, and all this, it's possible. And then in that time, they already said, now it's ready soon. But the lobbying was very tough from the chemical manufacturers. But nowadays, and even in Japan, in 20 years back, the prime minister by that time, he drove the first fuel cell car, and it had a CO2 system with the heat pump, actually. And they say it's 25% more energy efficient than the HFC system. But it never came because the lobby of the chemical industry was so tough. Even the emissions, you see the green bar, it used less energy. Even for a small car, which is typical probably in this country, at very high ambient temperatures, the CO2 system can be more efficient if you know how to design it. So there was actually no argument not to do it. And now finally, if you do a good job, you can buy this car. If you do a other job, you can buy this car. The ID3 and 4, they have the CO2 systems in Germany now. And in Norway, when they come to Norway, they have the CO2 system, even with the heat pump. So we are in a good way. There is hope. So we don't need these short life HFCs. There's some buses as well. Bus systems are there. Different brands, even in China. Railway also. And yes, railway and truck and trailer also. And truck and trailer is very interesting now because they're always between different standards and very difficult to which standard should we apply. There's this one German company. They kind of kicked a little bit the big ones on the knees. They do a combination. They have a system with the propane, no F-gas, on the roof outside, very efficient, energy efficient, and on the inside CO2, but no pump, just thermosiphon, and it works. It works very good. So they have a CO2 is then in cooling. It's evaporating here, condensing here, and it's circulating. In heating, opposite. It's just evaporating here and condensing here. Or it's condensing here and then it's rejecting the heat. But no pump, nothing. Works. And very compact. Flammable stuff is on the outside, no problem. Never in the compartment, and so on. If a leak happens, no problem. Carrier has this CO2 units in the containers. It's possible. So we see them coming. Hydrocarbons, I be quick. You see all this stuff on your rooftops everywhere also. All can be done with hydrocarbon. You don't need F-gases. It can be done safely. It's not a problem at all. There are different limits depending on location and so on. But if you follow the standard, it's safe. And these units are all with hydrocarbon. R290 mainly. Even big ones. Look at this. It's megawatts. 6 kilo charge per unit, and they have 77 kilowatt. And this is 1 megawatt, 50 kilo. On the roof, doesn't matter. If there's a leak, it will just went away. No problem. Here, they're even bigger. 2 times 1.2 megawatt, 40 kilo for 1.2 megawatt. It's very safe and energy efficient. Even inside, you can have it smaller units. And you see here, each unit has 2 kilo of charge. And the likelihood that all of them leak at the same time is 0. So it can be treated like this. So then you treat only the one with the maximum charge as the one which is corresponding for the room. And then it depends a little bit on, but it's all in the standard. If you follow the standard, you can do this safe. And you have to follow the same standard if you use these F gases, which are flammable. So there is no difference, kind of, from the restrictions. So it's the end user awareness, which is very important. Like you said, these potato guys, they don't know. But if they're aware, oh, we have a problem. We may have a reputation problem in the future. If they use ammonia, it's no problem. But if they would turn to something else, then we can help them to understand what is in the safety data sheets. What is it decomposing to? What is happening under legislation? What will come very soon? And we can do clean heating and cooling using these fluids. Nobody will lose the job. There will be more jobs, more than enough to do all these efforts. And yes, how to accelerate. One of my proposals is always that these investors, multilateral fund, governments and so on, they should support these kind of installations, because with a loan, because it can be, the payback will be the energy efficiency improvement. The less energy used, the people can use to pay back, and that would be a really sustainable development. Because they're often killed, these demos, because it's a little bit more expensive. But they could save so much more. But now that's not my budget. That's always the killer. That should be, that's what we try with our approach, to convince government to do this kind of programs, because that will really help. And in a summary, food is valuable for all of us, and that's what we need now and in the future. And it should be safe and reliable refrigeration equipment, not losing the food. And safety at work. We should not compromise safety. People doing the job, doing the service, or people are working in the area. That's the responsibility of the end user. And if he knows, I can do it safe, then he will do it, or she will do it safe. But if they don't know, if nobody tells them that this is a challenge, how should they know? And we know that we can use natural refrigerant and do it safe. And the impact is not only the global warming. That's a very, very important message. It's more. Be critical. What's in the bottle? Yeah, but how did it get there? What happened when it leaves the bottle? These questions are very important. If we have this focus, we have a good life. Yes, I think that was the last one. Yes, and if you have any question, we have this project together with other Indian institutes, but you're welcome to join. You're welcome to participate in the events we're doing. And whenever you want to come to Norway, here is my email. And soon we have a new colleague. So yes,